Good afternoon. So, last couple of classes we were trying to discuss about pericyclic reactions, right. So, what we did is that we took pericyclic reactions. So, what we said, we initially discussed about sigmatropic reactions. We discussed sigmatropic reactions. In sigmatropic reactions, we explained what is 1 comma n type of sigmatropic reaction. We explained n comma m. In 1 comma n sigmatropic reaction, we try to understand what is 1,3, 1,5, 1,7 hydrogen shift, methyl shift. We understood their stereochemistry by using suprafacial and intrafacial. And then in n comma m sigmatropic reaction, we went and saw how Claisen cope rearrangement takes place. So, these are all we covered in sigmatropic type of reactions. This is one of the important class of pericyclic reaction. After discussing on sigmatropic reactions, then we moved down to another important class is cycloaddition reactions. So, we understood cycloaddition reaction, we studied what is 2 plus 2 cycloaddition, 4 plus 2 cycloaddition, how it can be done in light as well as heat. We took reactions like Diels-Alder, we have seen as stereospecific, stereoselective, regiospecific and regioselective, and their applications also we did. Then later on we moved to 1,3 dipolar cycloaddition reactions and we studied their applications also. Once we covered cycloaddition reaction, then we slowly moved to another important class of pericyclic is in reaction. We studied in reactions, we studied different type of in reactions and the retro in reactions. So, these are the three important classes which we have so far covered in pericyclic reaction. We understood sigmatropic, cycloaddition and in reactions. Now, what we have to do is that we will try to understand other class of important reactions. One of them is, which you have already known, it is electrocyclic reactions. Once we study this electrocyclic reactions, then we will slowly move down to group transfer reactions. Then we will understand the another important class, that is your heliotropic reactions. So, and then one more which you can say it also falls under pericyclic reaction, that is your coarctate reactions. So, we have covered sigmatropic, we have understood cycloaddition, then we went to in reaction. Now, what we have to see in pericyclic reaction is we have to study electrocyclic reaction, then its group transfer, heliotropic and coarctate reaction. What I am going to do for next 2 or 3 classes, we will be focusing on electrocyclic reactions. So, these are what we are going to do in next 3 classes. Okay. Now, we will get into electrocyclic reactions. So, basically what's an electrocyclic reaction? How you define electrocyclic reaction? Simply saying it is nothing but it is a cyclization of a linear conjugated pi system. Nothing but it is a cyclization of your linear conjugated polyacyclic pi systems by forming a single bond. So, that is how you can define your electrocyclic reaction. So, if you want to show it in schematic, so you have a linear conjugated pi system. I will later talk on about how you can do the reaction, but if you have a linear conjugated pi system, they can get cyclized by forming a single bond. So, this is what we are saying. So, what I mean here, in net result, if you see your one pi bond, is converted to one sigma bond. So, that is your basic definition of electrocyclic reaction. You have a linear conjugated pi system under certain conditions like light, heat, which we will discuss later, they will try to cyclize, okay, by forming a new sigma bond. So, if you see the net result, you will be your one of your pi system will be getting converted into your sigma bond. Your pi bond will be converted into sigma bond. This is the basic definition of your electrocyclic reaction. Now, we will see some of the important things in electrocyclic reactions. The first thing you have to know about electrocyclic reactions are electrocyclic reactions generally they pass through an aromatic transition state. That is very important. This is very important, but that your electrocyclic reactions normally passes through an aromatic transition state. So, if you see this transition state, aromatic transition state, so if you see this cyclic transition state, so if you look into it, they will be either 4n or 4n plus 2 electrons will be involved in this cyclic transition state. So, what is your first statement? Your first statement, you are saying that electrocyclic reaction passes through an aromatic transition state. Then you say that in this aromatic transition state, normally the electrons involved are 4n, either 4n or 4n plus 2 system. Another thing about electrocyclic reaction is that electrocyclic reactions are generally induced by heat or light. So, to carry out an electrocyclic reaction, either you have to take the system, you heat the system, or other hand you can shine light on the system, so that you can undergo this cyclization reaction. And the one more important point which you have to remember is that your electrocyclic reactions are reversible. Okay. So, so if I take this part, what I am meaning is that these reactions are always reversible, okay, rather than saying they are reversible in nature. So, electrocyclic reactions are reversible. So, what we learned so far, electrocyclic reactions, normally it is a type of cyclization forming a new sigma bond on a cost of your pi bond. Then we said electrocyclic reaction can pass through an transition state, that should be an aromatic transition state, and this aromatic transition state involves 4n or 4n plus 2 electron system, and electrocyclic reactions are normally induced by your heat and light, and they are reversible. Mostly if it is a 3-member or 4-member reactions, they are highly reversible in nature. Okay. So, we will see some examples of electrocyclic reactions. So, you have a system. Okay. So, what is this? This is nothing but it is a butadiene. So, that we know that it is a butadiene. So, what system it is? Whether it is a 4 electron system or 4n plus 2? Yeah, it is a 4 electron system. Yeah, 4 electrons. So, it is a 4 electron system. Fine. So, once you shine light, okay, this can now nicely can cyclize to give you your cyclobutene. Okay. So, what I said is that now you get a new sigma bond, okay, in a cost of your pi bond. So, you have 2 pi bonds in the initial system. Now, you have a system where you have 1 pi bond and 1 sigma bond. Okay. So, that is your first point. The second thing is to remember that I already mentioned that these reactions are reversible. Fine. So, again this reaction can get back to your starting material to give me cyclobutadiene. So, it is a reversible reaction. And third point, you have to remember that this reaction goes through a transition state, cyclic transition state. So, I will explain that in detail, the transition state and all. Now, just for example, we can see this is a 4 electron system. We will take another example, which is this is cyclohexatriene. Yeah. What electron system is this? Yes, it is 6 electron system. So, it is a 4n plus 2. So, you know it is a 6 electron system. Similar way, when I shine light or when I heat this reaction, so this reaction can cyclize, giving me you. Again you can see initially I had my 3 pi bonds, now I have 2 pi bonds with a 1 extra sigma bond. Okay. And same way these reactions are also reversible, okay, to give me back my starting material. So, you can reverse these reactions to give you the starting material. This is 6 electron systems. You can also have an 8 electron system where you can think about your cyclooctatriene tetrahedron system. This is what this system is, your 8 electron system. So, again it is a 4n system, right, 4n, yeah. So, as I said, so now I should get my product should have 3 pi bonds and extra 1 sigma bond. So, I have a 3 pi bond with a new sigma bond, and as I already said, these reactions are reversible to give me my starting material back. So, these are the some basic example of your electrocyclic reaction. One, we have seen your 4 electron system keeping your butadiene, and then we slowly went to your 6 electron system, and then we have seen your 8 electron system. So, now this is a basic idea of your electrocyclic reactions. The interesting point of electrocyclic reaction comes when you start understanding this reaction stereochemistry. That is where the beauty of your electrocyclic reaction is. They are very concerted, okay, very specific in nature, and you get one type of product. That is really interesting one. So, to understand that, first we have to understand the stereochemistry, and stereochemistry, you know that for understanding the stereochemistry of electrocyclic reactions, you have to know the molecular orbitals. Without that, it is very hard to understand them. So, what we will do, we will take a general system and try to understand the stereochemistry first. So, now we are slowly getting into the stereochemistry of or electrocyclic reaction. Okay, then consider that I have a long Pauling system. So, I want to cyclize this. For example, this is my substituent B and A. I am talking about the edge of my alkene, okay, the double bond. Fine. So, I have A and I have B. Fine. So, I want to do the cyclization. I want to bring them together to form a sigma bond. So, I can think about two possibilities. One possibility is that I can move across these two bonds. Okay. So, what happens if I do this? So, I get a system like this. Please now carefully watch your substituent, that is the most important part. Now, the interesting part is that this B and A, this is the substituent which you have to. Now, I have just flipped this molecule in a clockwise direction. Okay. So, what will happen? This B will move up. So, I have my B here, then I have my A down. Clear? Same way, I am just going to move this molecule in this way. Okay, this orbital, sorry, this orbital in this direction. So, what happens? I get my B here and then I get my A. Fine. So, what bonding? This is a proper bonding orbital. Fine. You can ask me, sir, why cannot we do in other way around? Why you have to mix this? Can we think about this direction? That is, I am B A, same system. Okay, I have a same system. Okay. Now, instead of doing like this direction, if I can do in other way around like this. Fine. So, what happens now? Now, what will happen is, so guess it is right that and I am flipping up this. So, my B should be here and my A should be down, and I am flipping this guy up. So, my A should be up and the substituent B should be down. But this is what? This is not, this is what? This is anti-bonding, right, interaction. So, this is not going to happen, right. So, my approach now in this case, what? So, this is the only approach which gives me a sigma bond, right. Now, get into the direction in which I have rotated this orbital to give me a bonding thing. See what direction it is? It is a clockwise, fine. This one anti-clockwise. So, you have here two types of movement. One is clockwise direction, another is an anti-clockwise direction. If you have clockwise as well as anti-clockwise rotation to give you a sigma bond, then you call this rotation as disrotation. What? Disrotation. If you have like clockwise and anti-clockwise, or either way, anti-clockwise or clockwise, you call it them as a disrotation. Clear? This is very important. Okay, this part you should know. This is called disrotation. Now, we will take another system, same way. So, now I am taking the same one. Okay. If I get a scenario like this, okay, I have a system like this. So, again you can think about your two possibilities. So, I will just draw the substituent so that Okay. Now you think about what happens. So, in this case, to create a bonding, I have to either move this and I have to move this, right. Then I will get a bonding or bonding thing, which will be so now the substituent, think about your substituent, that is the more important part. So now you are flipping up this, so my A will go up and my B will be down, and in this direction again my B will be in the thing and my A. See, in the previous case, if you just try to relate the previous one where you will have both B in the top and A will be the same, like cis type of. In this case, you get a trans type of thing. That is why I said the stereochemistry of your pericyclic reaction is very important. Yeah, we will go with the substituent. First, you understand this basic schematic, how you represent them. In this case, again, yeah, you can think about another mode, which is your dis, which I told you already. This is clockwise and this is anti-clockwise. Then you call them as a dis. But this will not give you the what, because this will be more like your anti-bonding. Your B will be up and your A will be here. Your B will be up and your A will be up. So, what happens in this case? This cannot happen because you know that. So, this is not going to happen for you. So, only this is happening. Fine. Now, think about the direction. So, this case it is what? Anti-clockwise. This is also anti-clockwise. So, if you have both anti-clockwise or if you have both clockwise, okay, then you call this rotation as con rotation. Okay. So, this is more important point to remember. If you have one clockwise, another anti-clockwise, you call them as a dis rotation. If you have clockwise, clockwise, you call it con, or if it is anti-clockwise, anti-clockwise, you call it con. Say if it is the same, then you call con. If it is different, then you call it as dis. Clear? Okay. Because keeping this in mind only, we can go for other reactions, we can step on many other problems of pericyclic reaction. This is very important. If you have any doubt, please let me know. Fine. So just to then summarize, so con rotation is nothing but, I can say it is a either clockwise direction rotation, clockwise plus clockwise direction, or it can be anti-clockwise plus anti-clockwise. And your dis rotation is nothing but it can be anti-clockwise plus clockwise, or it can be vice versa. Fine. So, this is the stereochemistry of electrocyclic reaction. Now, based on this, we will see how we can slowly understand the 4n plus 2 rule and 4n plus 2 and everything. Now, we will take this system and the same analogy we will try to apply to your 4n system. Okay. Then we will apply the same analogy to your 4n plus 2 system. So, first what we will do is that we will slowly get into your 4n system, that is take your 4n electron system. Okay, we will take the simplest system of 4n electron system. Yes, your butadiene. Yeah, we will take your butadiene. Now, we will try to understand how in butadiene we can think about this dis and con rotation. Before getting into butadiene and understanding its stereochemistry, I have teach you the molecular orbitals of ethylene, butadiene and cyclo XR train, but it was long ago, right? You would have forgot. So what we will do is that we will just check it, refresh ourselves back. I will show you the butadiene bonding, anti-bonding orbitals. Then after knowing that, we will get into their thermal and photochemical reactions. Fine. So we have studied this. Anyhow, let me again I will just let you know there. Fine. So this is your, we can call it as pi 1, that is your bonding. Then you can have one more. So it should be 2 down. We can call this as pi 2. Again, yes. And then you have your, this is your bonding thing, you know that. And then you have your anti-bonding. So I can call this as pi 3. Then I have my pi 4, right. So we will just share it off. So this you can, this is your anti-bonding. So this is your system of butadiene which you have already studied. So this is your pi 1, pi 2, pi 3 and pi 4. The thing which you have to carefully notice is that your pi 2 system, okay, and your pi 3 system. Your pi 2 system, which you can call them, which is nothing but your HOMO, highest occupied molecular orbital. Whenever I talk about pericyclic reaction and if I shine light, okay, and that means I am doing no, whenever I talk about the pericyclic reaction in thermal condition, you keep your HOMO should come into your picture, HOMO molecular orbital of your butadiene should come into picture. But once I start talking about your photolytic, then your pi 3, that is the LUMO, should come into your picture. So this thing you have to remember. See, in HOMO case what happens, that this last two one, this is your opposite and this will be your same one. So this part you have to remember before you. So keeping this in mind, now what we will do, we will see the reaction how it works in butadiene. Now we will do the thermal condition. Now I will take 4N per system. So I will take butadiene because it's a simple system. So I take butadiene. Now I will just understand its stereochemistry in thermal condition and see whether what happens in thermal condition. So I have a cyclobutadiene. For example, I will just go with the orbital. This is going with orbital is nice molecular orbital because that helps you to understand things very easily. Okay. So I am doing a thermal condition. So what I have to remember? I have to remember my thermal condition, what? Pi 2 system, right, which is the HOMO. So I have written the HOMO of my butadiene. Now we know that the reaction should give me a bonding orbital only. So we said that anti-bonding is not allowed. So if I want a bonding, then I need this direction to take place, right? This should be my direction. So if it is that case, so I have to draw. Now tell me what rotation is this? This is what direction? Clockwise. This is clockwise. So what we studied, if we have clockwise as well as clockwise, then what rotation you call them? Yes. What rotation? Yes, it is con. So we call this as a con rotation. So the first point is that if you have a 4n system, see I am taking butadiene, but I am talking about 4n system, clear? So what I can understand from here, if I take a 4n system and if we do heating, then my reaction should proceed through con rotation, clear? Okay. Now we will see photolytic condition. If that is photolytic, you know, yeah, you take the reaction and shine it with the appropriate wavelength of the light, fine. So we will see what happens in photolytic condition then. So if I say photolytic condition, what molecular orbital of your butadiene you should think? Yes, pi 3, very good. Pi 3, that is your LUMO, lowest unoccupied molecular orbital. So how it looks like? So this is your pi 3, that is your LUMO which you are talking about. Now if I want, this is on h mu, which you know that you represent for light. Now what direction? Yeah, I can make this like this, fine, to give me my orbital. So one is clockwise, another is anti-clockwise. If you have a clockwise and anti-clockwise, what we said? Yes, we said it is a disrotation. So what you learn now from this system? What you learn? So if you have a 4n system and if you heat the system, the reaction takes only one mode of approach, that is your con rotation. In same way, if I shine light, then the reaction takes the other direction, that is your disrotation. So 4n heating gives you con, 4n light gives you dis. Clear? Clear with this? Any doubt up to this? Fine. So now we will take 4n plus 2 system and see whether we can think about the same part. So we will take 4n plus 2, fine. So for 4n plus 2, I will take the simplest example. Yes, I can think about my hexatriene. So I can take that as my simplest example to approach hexatriene system. Okay. Same way, before getting into understanding the thermal and photoelectrical condition or whether it is con or dis, we will see the molecular orbital of your hexatriene system. So we will draw the molecular orbital for our understanding. So this is a pi 1. First I will try to draw your bonding. So this will be your bonding orbital, right? So that's we can call them as pi 1, pi 2 and pi 3. So this 3 will be your bonding. So you will be talking about your electron systems here. So, if we find out what this we know, in this case it will be 3 up and 3 down. Here it will be 1, it will be up, then it will be down, it will be up, right. So, this is your bonding system, and we say that this is the part which you are going to be much worrying about, your HOMO. Okay. So, when I am going to talk about your thermal condition, you are going to think about your pi 3 system, which is your HOMO. Okay. And you know antibonding, you can again draw 3, which I have already shown. In this case, I am just going to draw you one system which we will be studying. Fine. Fine. So, this is your pi 4 system. This is the LUMO. See, you have pi 5 as well as you have pi 6 system. I have not drawn in this case, we have already discussed that about how pi 5 and pi 6 looks, but for our understanding, we will be concentrating more on your pi 3 system for thermal condition, because that is the HOMO, and then we will be concentrating on your pi 4 system for your photolytic condition. Clear? Okay. So, now you know the molecular orbital of your cyclohexatriene systems. Yes. Now, we will see how it works in heat and thermal and photolytic conditions. Now, we will take cyclohexatriene system. So, we will say that we will do this reaction first in thermal condition. Okay, we will do it in thermal condition. So, as you know, in thermal condition, what you have to consider? What orbital we are talking about? Yes. Anyone? Yes, pi 3, the HOMO, that is your pi 3 system. So, you just draw that. So, your pi 3 is see, first initially once you want to learn, you put all the orbitals, try to understand, then once you know, keep on after doing several exercises, then you can work on these 2 last orbitals and find out your product for exams and all these things. But I think initially you should try to draw orbitals of all these complete structures, then you can slowly move on. So, that is your pi 3 system. So, this is in heating. So, what we can think about, whether you get a cone or this. So, this I can, because I am interested in bonding. So, right. So, fine. So, what direction is this now? One is, yeah, you guys know it. So, direction is not a big thing. This is clockwise and another is anti-clockwise. So, this is nothing but, yes, this rotation. See, if you can think back and if you can understand what happened in foreign system when we were doing heating. Yes, when we are doing heating in the foreign system, then it was a con rotation. You see, in this case we just get the reverse of it. So, we get a disrotation. Now, we see what happens in the photolytic then. When you do photolytic, then what you can expect this to happen? Well, just put your orbitals, that is all. That will tell you whether it is a dis or con. Okay. So, photolytic means what you have to think? Yes, yeah, pi 4, that is your LUMO system. Just draw that. Fine. Now, just finish it off. I said it's initially it is nice to you put all the things, later on you can think about the last 2 orbitals. Yes. Now, this is in light. So, yes. So, what happens now? Direction, if you just look into the direction, one is clockwise, another is also clockwise. So, what we said, clockwise, yes, con. So, clockwise will be con, anticlockwise is also con. If you have difference, that is clockwise and anticlockwise, then you go for this. So, this is a con rotation. Again, if you just remember what happened in your foreign system it was opposite this. So, foreign, if you take the system and heat it, you end up with a con rotation. Then if you shine light, you end up with a dis. But once you go to foreign plus 2 systems, you just get the reverse of it. That means, when you heat it, you get a dis, and when you shine light, you get a con rotation. See, this all was, this whole thing was formulated by one of the great eminent scientists, that is Woodward Hoffmann. Okay, you cannot forget. So, we will just get Woodward Hoffmann rule. Now, we see what whether it is going right with this. So, your Woodward Hoffmann rule. So, you have to see number of Woodward Hoffmann rule. Okay, number of electron system, and then just see mode of reaction. Then you can always talk about whether this is allowed in thermal and photolytic. You can make a table like this. Nicely make a table and see whether it works on this. Okay. If I take a 4N system, fine, I am taking a 4N system. Now, mode of reaction. So, I am saying 4N system con, okay, which is in heating allowed or photolytic it is allowed for 4N system. Just think back, yes, heating 4N system goes, photolytic it is not allowed. That is what Woodward Hoffmann rule says to you. Then 4N, if I want a dis, in which it is allowed? It is allowed in thermal or light? Yes, it is allowed in photolytic condition, thermal it doesn't work. Now, go to your 4N plus 2 system. Again I am saying con, in which system it is allowed? We have said that In 4n and 4n plus 2 system, it is just exactly the reverse of it. So, in 4n plus 2 system con, yes, in heating it is not allowed, it will be the reverse. So, it will be allowed in the photolytic condition. So, 4n plus 2 system, then if it is dis, then yes, it is allowed thermally, it is allowed photolytic. So, this is your basic Woodward Hoffmann rule. So far what we studied is that we took electrocyclic reaction. We said that electrocyclic reactions are nothing but it is a cyclization where your 1 pi bond gets into a sigma bond, and this reactions goes to a transition state which is aromatic type of transition state, and the number of electrons which you have seen is 4n or either 4n plus 2 system. And then we said that these reactions are reversible, which you have already seen, and these reactions are either done by light or heat. And then we saw the examples how it works in butadiene, cyclohexatriene and cyclooctatriene. After studying that, then we went to the real interesting part, that is your stereochemistry. And we said that if the closure, ring closure goes clockwise, that is the same direction, go clockwise or anti-clockwise, then you call them as con rotation. If it goes clockwise as well as anti-clockwise, that is two different things happening in the ring closure, then you call them as a disrotation. Then we took a 4n system and we studied that in 4n system, in heating you get only con, and if you go for light you get the reverse, that is dis. But when we went to 4n plus 2 system, we saw entirely the reverse of your 4n system, and then we just formulated your Woodward Hoffmann rule. Clear? Okay. Now what we will do, this is the basic part of your pericyclic, that is electrocyclic reactions. Now we will take some examples and try to understand this. That will be really nice to see that. For example, I am taking this system. Okay. Now I have a now I have brought some little bit interesting fact of substituent into it. If it is simple cyclobutadiene, yeah, you do not understand much about its dis or con. When it is a substituent, now you will understand how it is important. So what is this? This is your butadiene where you have like Z and E, Z as well as E. Now I have taken a system of Z and E. Now I say that I am giving you this system and asking you to heat this and see me and tell me what cyclized product you are getting. Okay. So this is on heating. So first, when you are starting things, first thing you have to learn how to know is that, see, you know what it is? It is a 4n system, right? It is a 4n or 4n plus 2. It is a 4n system, that you first figure out. I have given you heating. So 4n system heating, I said you should think about your pi 2 system, that is your homo. So how that last thing, just remember that, okay. So it will be just the opposite one, right? If you think the last of the orbital, so that's what you get in 4n system. And now if you shine light, so I can move this guy up, and because I want to make a bonding. And what rotation is that? One is clockwise, another is also clockwise. It is a con rotation. So it goes nicely with your Woodward Hoffmann rule. So 4n system heating con rotation, it is allowed. So the reaction goes nicely now. Now see, just I have moved this, so I have to draw it. Once you move this direction, just look your substituent, just is tilting, so that means your hydrogen goes up. So I have my hydrogen here, now I have my methyl here. In this case what happens? You just tilt this, okay, the whole orbital just spins, so your hydrogen goes up. So your hydrogen goes up and you have a CH3. So what is this? So you have now 2 methyl in the same side. So this is your cis. See, you get one product. Reaction is very concerted and you get a one product, that is your cis one. Fine. See, the interesting part now comes. If I take the same substitute, same reaction, okay, this is the same ZE. I take you the same ZE. Okay, just let it be. Now I say that I am taking the same ZE, but I am going to do this reaction instead of heat. I am going to do this reaction under light. I am just going to shine it off. Previously I said I will heat this reaction. Now I am saying this, I am going to shine the light on this same substrate and see what happens to this substrate. It is the same substrate. So, once I say light, what you have to think? Now you do not think pi 2 system, now you think about your pi 3 system, right, that is your LUMO. So, how your pi 3 system then looks about? It looks in this direction. So, I can just move this guy there and can get you this. Now, what happens? So, what rotation is this? One is your clockwise, another is your anti-clockwise. I said one clockwise, another anti-clockwise is nothing but what? Yes, it's nothing but it is your this rotation. Now, you see the stereochemistry. Once you add, once you close this ring. Oh, sorry, I missed a double bond here. Okay, because it's a cyclobutene system, because you have to get your double bond there, right? Yeah. So, what will happen now? So, in this case, my hydrogen just goes up. So, I have a hydrogen, I have methyl. In this case, what will happen? So, I am just doing this other way around. So, my methyl goes up, my hydrogen down. Now, what happens? Now, I get an just exactly opposite product, right? I get a trans. See, that is how the electrocyclic reaction becomes really interesting. You take the same substrate, okay, the ZE butadiene you are taking. Once you shine light, you end up with a cis product. See, once you heat it, you end up with a cis product. But at the other hand, if you shine light, you end up with a trans. That is where it is really interesting, these reactions are. So what happens? The same system you can work with different examples. I can teach you. I can tell you one more example. It's the same thing which you can think about. Is that okay? What system is this? In previous case it was ZE. This time it is ZZ. Okay, I take this system. Now I say heat. Okay, I know now it is nothing but it is a con rotation. Okay, so I know the direction in which I have to go, con rotation. Hydrogen, methyl, and I get my methyl up, hydrogen. See, in this case I get my trans. ZE con rotation gave me cis, ZZ con rotation gives me trans. Same way, if you take the same substrate and see what happens in light. Because they are this rotation, light. So, you have H and you have CH3. Now, it is you get a cis product. See, that's why I said that stereochemistry part of your electrocyclic reaction is so nice. You took ZE, you do the heating, con rotation, you get a cis product. You take the ZE, do light, you get it trans. But in this case, you take ZZ, okay, and then ZZ butadiene, ZZ butadiene, and then you do the heating, you get the other way around, you get the trans, and once you shine light you get a cis. So that's about your 4n system. In this class what we will do, we will try to understand your 4n plus 2 system the same way we did. Then we will try to do ring opening also, because we said that reactions are reversible. So, we will see some examples of ring opening, then we can work on other more examples of 4n and 4n plus system of bigger molecules and see whether we can go for that end. Okay. So, with this we end this class. Thanks.